All right, line V1, we're on learning task number 6, where we're going to go and take a look at the diagramming of magnetic starters. And what we're going to do is we're going to go and start by just going through a number of components that we're going to look at, and then we're going to take a look at schematics, and we're going to compare those schematics to our wiring diagrams. Schematics are going to be the easy to follow ones that we are used to. This over here is a schematic over here. This over here is going to be an actual wiring diagram, which is going to contain the exact same components, but it's going to be done in a way that's going to be more pictorial than what we might necessarily be used to. So we're going to work from changing from this, which is what you would use inside of the field to play connect the dots, it's a visual representation, over to this over here. But let's start by taking a look at the actual components. These table number 1, and I've broken it apart into 2 so that it's large enough for us to go and take a look at, is going to be a set of symbols that we're going to use inside of schematic diagrams. In wiring diagrams or pictorial diagrams, we're going to be using actual pictures, like those contactors that I've been showing you a couple of times through here, the overloads and things like that, stuff that is representative of the field look. But this is what we are going to use when we're drawing out our schematics. Okay, what I do want to go and point out as well is that all of my switches are shown at default in their at rest application. In other words, if this is a normally open switch over here, we would go and show this thing at rest. My direction of movement for every single one of these as well is also going to go and be in an upward direction. If you take a look, you'll see this section down here. We call this the operator on every single one of these. You'll see that the operator is always sitting below that line. And so what we are going to have is during activation, the operator is always going to get pressed in the upward direction. In other words, for this pressure switch over here, it's a normally open pressure switch. I see that it's a disconnected line over here. That is going to, on an increase in pressure, it is going to go and close. This one here is a normally closed pressure switch, which means that on an increase or an upward direction of pressure, this thing would then go and open up. Same with my float switches, also referred to as liquid levels. We can draw the water in over here. We would see that if the water moves in a upward direction, the normally open would close, or that my normally close, if the water would move in an upward direction, would push the float up and it would open. These are symbols that you need to be familiar with inside of our trade. These ones over here are going to be my limit switches. Limit switches are going to be drawn with that little triangle on the bottom. Now, limit switches are going to go and have a double state. Actually, all of these have a double state. So this box that's down here is a tricky little box to understand initially. Because what this is this is a held closed type of position. This one, although we see that the connection across there is an actual closed connection. We can get current through from one side over to the other. This is not a normally closed switch. What we would refer to this one as a normally open. Remember that it's underneath here, which means that it's going to be normally open. My normally closed are up top, like that. So we would actually refer to this thing as a NOHC. We add that HC designation behind it so that we understand that this is a normally open held closed. It's kind of difficult to understand maybe on the limit switches. It's an easier application to understand on a float switch over here. Let's take a look at the float switch. Let's pretend that this float switch is inside of a pit. Okay, I'm going to go and take, we'll just draw a pit over here on the side. We're going to take that normally open float switch. We're going to go and draw in 2 separate float switches over here. Here. And we're going to go and draw in one over here. Start by drawing the 2 little dots. That's going to be the contact points. And then I'm going to go and have this over here. So it's going to be a normally open float switch, right? We all identify that as being a normally open float switch over there. This one over here, I'm going to go and have as a normally open float switch over here as well. Okay, so I've got 2 float switches inside of this pit. Let's start filling this pit with water. Bloop, 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 bloop. Just like that. We see that this float switch, as we increase the water level, that float is going to move in the upward direction. And eventually what happens is that our process variable, that's a fancy term for the thing that we are controlling. So over here, my process variable moves up to a point where it is going to go and permanently hold my switch. At this point, when this thing is underwater, it is a NO, normally open, held, closed, contact. What is holding it closed? The process variable. For any one of these switches that I have in here, we can have a held, closed type of condition, right? I could have this one over here, the normally open pressure switch, that I could have a high pressure that would be holding it closed. And I would designate it as an NOHC. How do I know that it is a normally open, held, closed compared to a normally closed? It is the side of the line that it's on. If it's on the top line, it is a normally closed. If it's on a bottom line, it is going to be a normally open. We've also got this other designation of a held open type of switch. The held open would be the opposite designation. I'm going to go back to this one that we have drawn down here, and we're going to go and place in a set of normally open float switches over here. A normally open float switch would be sitting like this, normally, but then, normally open, normally closed float switch. I'm talking to myself wrong over here. Normally closed float switch would be sitting like this. And this one over here would also be sitting in the same manner. But as soon as we go and provide the activating force, once again, referred to as the process variable, once we put the process variable into here, that thing is going to go and start to float up, right? We'll move our water level up to here. At that point, the water level would be pushing this float upwards, and as a result, this normally closed would be held open. We would refer to this switch over here as a NCHO. Normally closed, because that's going to be its default position, held open. Remember that we are always looking at our process variable, pushing the thing up. So you just assess, based upon the switch, is the switch on the top side of the line or the bottom side of the line? Let's go back up to this one over here. If it's on the bottom side of the line, it is a normally open. If it's on the bottom side of the line and it is pressed up against it, it is a normally open, held, closed, NOHC. If it is on the top of the line, it is a normally closed contact. If it is on the top of the line and it is open, it is a normally closed, held, open. Okay, you're going to have to remember these things later on once you get into some motor control, particularly in pumps. You know, it's a really commonplace. People want to have stops as normally closed, but the problem is if your stop is usually going to be at the bottom of the pit, because that's what you're doing if you're pumping water out of it, but it would always be held open and stuff. So you have to sometimes refer to these things when you're actually looking at them in the field. We don't get into that yet this year. That's going to be something that's going to come about in fourth year. So for now, we're just going to go and leave them with the identification. A couple of others that we are going to go and have. We have got what are referred to as motion switches, also sometimes referred to as centrifugal switches, or as zero speed switches. Let me just erase that as well. Both of those are going to be designations off of those motion switches. Foot switches, which have got the little operator here on the top. Pressure, which is the half circle. Liquid level, which is the full circle. Temperature activated, what we refer to as a thermostat, which is going to go and have this, squared out zigzag line over here, representative of the bimetallic strip. Flow switches, which look like a little flag blowing in the wind or the water or whatever you want to go and have. Then we're going to move into protection. Fuses, which are going to be like that. Now, fuses are a squiggle line that's an actual sinusoidal line like that. Overloads look somewhat similar, but they're going to be two completely separate C's like that. They don't join in the center over there. Okay, this is going to be your OL. This is going to be your OC, overcurrent, or your fuse that you would go and have. Okay, just make sure you differentiate those. Circuit breakers are going to be done with those, so that's for our protection. Fuses can be drawn as a square. I usually draw them just that squiggly. That's too many lines for me to draw otherwise. That we are going to have disconnects and circuit breakers, by the way. Anytime that we see that dotted line across the middle, that means it's operating off of a common bar. They've got a single handle, so that one would be a 3-pole circuit breaker or a 3-pole switch that we would have. We will have 2-position switches. They will not always be labeled as hand and auto, but it's pretty common that we're going to have them. And then 3-position switches, which go in between 3 positions. We have a hand position, we have a center off position, we have got another auto position over here. Once again, hand off and auto are not always going to be the designations, but in a lot of cases they will. We do also have 2-position switches that are going to go and be maintained ones over here where we've got sets of contacts. We will sometimes see these same switches here drawn in this, but these are going to be a push button activation. These ones here are actual, toggle switches. These ones here are going to be a push button activation that's going to be on a panel. It's really just a bit of minutia. What I do like about this one is the fact that it shows us the tabling of information. What we're seeing inside of here is that if I am in position H over here, it shows me that my contact point A1 is going to be closed. Position H shows me A1 is going to be closed. If I take a look at position A, we can read the same thing. In position A, I see that my A2 position is going to go and be closed. The big difference between the contact closed and between the two position that we see up top here is that the two position has got a common off of it, feeding in, right? So I can only feed in one value of volts. Let's say it's 120 volts into there. And then I could take 120 volts out here and 120 volts out here. But in some cases, we're going to go and have multiple levels of voltage that are going to have to go through the same position. So what's useful then is on something like this, I can feed in a low value of volts, 24 volts, that's going through maybe my hand position. And in my auto position, I might be feeding in a different value of voltage, 120 volts. It's the same physical, control button that you're going to see on your panel, but we've got what we refer to as dry contacts or isolated contacts rather than a common contact over here. If I wanted to convert these ones into a common contact, all that I would do is run a jumper. Just like that, and at that point, it is essentially the same thing as the two-position switch that we're going to have. My three-position, exact same thing. This one over here, my three-position switch, has got a common. This one over here has got now individual dry contacts, and you can just read them off the chart. When we're in the open position, neither are closed. In the hand position, A1 closes. In the auto position, my A2 is going to go and close. Meters, we've seen those a million times. We'll skip past that. Let's take a look at our push buttons. Push buttons are always going to be seen as a downward force that we are going to go and put on them. Okay, that's going to be opposite to the way that these switches that we saw over here, these switches were always an upward force. Push buttons are always going to be in a downward force. So when I push a normally open push button, that is going to shove that thing down like that. If I push on a normally closed, it is going to go and shove that thing down like that to go and make it into an open, etc. We do have some that are going to be double contact, where I'm going to go and have a normally open, normally closed off of these ones as well. If you take a look at this one that they have over here, the NO and C is all part of the same thing. My normally open would be the bottom two that I would be looking at. My normally closed would be the top two. It's very common where we have that where it changes over from one to the other. Mushroom head buttons are going to be those big red stop buttons that you see that we use for emergency stops. Some cases we're going to have push buttons as well that are going to be tied to a pilot light inside of them. Maintain contact switches are going to go and have an activator that is going to go and pop out one button when the other button goes down. So this over here, that dotted line, is indicative of a fulcrum, having that little piece there in the bottom. Basically, if I would push this one down, then that is going to go and push this one up, and vice versa. When one goes down, the other one would have to go and mechanically be changed out. That dotted line refers to mechanical interlock, as it's called. The double circuit one, by the way, is just missing half of the drawing. I don't know where the rest of the dots went off of that one, but it should have the exact same symbol over here that's going to be on this side over here with a number of these. So we'll just draw that in there. That's where my push button would be right now, because that one's at the top side, this one's at the bottom side, and when I push that, they're going to go and alternate. Pilot lights. Pilot lights are going to go and have non-push to test, or what we refer to as just a standard pilot light. We will also oftentimes have push to test. So this one might be where I'm taking my signal in. That's usually going to turn it on. But this line over here might be my constant voltage. Okay, I'll just put a plus V over there, so that if I want, I can just push this pilot light. If I want to know whether the pilot light is burnt out or not, I can literally just walk up to it, press it. It'll take it right directly to the full value of voltage. We'll say that this is going over to neutral. And then that would allow me to double check and see if it's a burnt out pilot light or if the actual load itself isn't on. Really handy when you've got sealed processes, stuff that is happening inside of a pit that maybe you can't get into, or inside of a drum or something like that. You want to know if the heater is on inside of the drum. You can't just open it up because you got a process under pressure or something. You can push that push button and say, yeah, the push button is not calling for it, so it must be off, but I can check that my circuit is correct or that my light bulb isn't burnt out. Less common these days that we are going to go and have that because we've moved obviously all into the realm of LED controls. But years ago when we had incandescents, incandescent bulbs were a major problem. I would get calls from customers that would say, hey, this thing isn't working. Can you come here and check? And I go there and the thing would be working. They'd be like, but the light's not on. And so I'd pull out the light bulb and you replace the little incandescent light bulb. We just have that less common at this point. We do still push to test, but it's less commonly needed at this point because we have such long lifespans. Contacts are going to be defined as being normally open or as being normally closed inside of here. They're going to be drawn as being two separate lines that we are going to have over here. And then we are going to go and have a crossing line that's going to stand for normally closed. I know it's very similar to one of our symbols for a capacitor. Capacitors can be drawn in the same way with two lines like that, straight lines like that if it's a non-polarized capacitor. However, most of the time we just draw in a polarized capacitor inside of our drawings just to designate that it is. Even if it's a non-polarized used on AC cap, we'll often draw that in just to differentiate the cap from the actual contact points. Time contacts. Okay, this is a tough one over here. It says time contacts or contact action retarded when coil is energized or de-energized. This is a technical term, retarded. I know it's a word that not everybody is familiar with, but when used inside of a technical application like this, it applies. What that means is it means slowed down. That's the English definition of it. You will see it on a lot of control diagrams. They're not trying to make a joke or be ridiculous or anything like that. They're just trying to say it is slowed down. So what we're seeing over here for all four of these is slowed down sets of contacts. Looking at these, I see that that is a normally open, just looking at that bar. Looking at that, I see that as a normally closed. Looking at this, I see it as a normally open. Looking at this, I see that this one is a normally closed. And so I work off of those, the NO and the NC, and then I'm going to go and define what they're going to go and do. Now, we don't cover these a lot in this year. We will cover them in subsequent years. But the direction of the arrowhead tells me about when I'm either turning this thing on or when I'm going to be turning this thing off over here. This one is going to be a contact that when I energize the timer, it is going to be delayed. We refer to this thing as an on delay that we would go and have. So I'm going to go and provide energy. We'll just say power. Then there's going to be a time period, ... whatever it's set on my timer, and then activation that we are going to have. That's what we're seeing inside of these ones over here. I'm applying power, they're going to wait, and then they're going to activate. So this one over here is going to be normally open, timed to close, right? We apply power, it is normally open, it waits, and then it activates. It's going to go and close. We're going to refer to that symbol as a NOTC. NOTC over there. This one over here is normally closed, but when we apply power, it's going to go and wait, tick, 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 and then it's going to go and activate. This is going to be a normally closed, timed to open contact that we are going to see off of that one. This next group over here is going to be a little bit more tricky. These are going to go and be my off delay. This was what we refer to as the on delay category. On delay. This one over here is going to be my off delay category. I'll draw them with a blue marker over here. The off delay are going to be different in that when we power them up, then they are going to go and instantly activate. And then when we go and depower them, they're then going to go and time to go to rest. So they're basically timed to rest. I'm actually going to remove that whole top part because that's going to make it too confusing. Let me just lay out the contact points. So power, they instantly activate. Then they're going to stay activated. And then when we have no power, then they are going to start their timing. Tick, tick, tick. And then they are going to go back to rest. Okay? It's a more complex, it's tough to go and understand the first couple of times that you deal with these things. But if I take a look at this thing, my normally open, when I apply power to the timer, the first thing it is going to do is close. Well, when we activate normally open, it's going to close. So it's going to close over here, and it'll stay like that the whole time. We applied power, it closed. When we take away power, it is then going to stay in this position because it's timing. Tick, 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 tick. And then at the end of the time, it's going to, boom, go back to its rest position. Let's look at this one over here. Once again, when we apply power, it will instantly activate. Boom, it's going to push open like that. Then it's going to stay open for as long as we apply power, but when we take that power away, then it's going to start timing. Tick, 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 and then, boom, go back down to the rest that we are going to have. This one is going to go and have a separate designation. This is going to be referred to as NOTO, normally open, timed to open. Really, it's time to reopen is, the better way to say it, but it's an NOTO. This one over here is going to be NCTC, normally closed, timed to close. So it's normally closed, timed to reclose is really what it's going to be. Upward arrows, really easy to go and work with. The downward arrows, a little bit harder to go and deal with when we're dealing with our time. All right. Let's look at the next one that we have over here, which is going to be coils. We've seen coils before. They're going to be drawn as a circle. Usually we're going to have, terminal designations on either side. Overload relays. We've talked about overload relays before, that they're going to be that hook shape that we're going to go and have over there. And then they're oftentimes going to go and show a link that is going to go over to a normally closed set of contacts. This is the actual heaters. This is the actual set of contacts that we are going to go and have. Mechanical connections, mechanical interlocks are going to be done with these ones. Mechanically connected means they all move together. Mechanically interlocked means that they change. Like these ones here, see they got a little ticky over there? That means that they got the mechanical interlocks, so they're going to change. Whereas these ones here have got just the dotted line together, which means that they're going to go and activate together. Okay, transformers are going to be down here. We've got auto transformer, iron, CTs, dual voltage, etc. We've covered that stuff inside of transformer action before. Single phase motors and three-phase motors, oftentimes drawn like this. They oftentimes also will go and have a small triangle drawn onto the bottom. That also designates them as a motor. It's an alternate symbol, as we refer to it. Connections in lines or in wiring. We have got connections which are always going to be done with a dot. Not connected can be like this. Now, there's a way to make it even clearer when it's not connected. That's going to be referred to as my hop type of convention that we would go and use. That shows that those are definitely not connected. When you are writing exams and making drawings, I require that you're not connected are going to be done with the hops, and that you're connected are going to be done with the dots. Because other students in the past have screwed that for you. I've had students in the past that have made sure every line crosses with another line, then afterwards they come to me after a test and they're like, actually, I should get the mark over here because you can see that these lines were crossing over here, which meant that I actually had meant that these ones were a connection, and I hadn't meant that these other ones over here, which are also crossing, are not connections. And it's super annoying because you know that they're just grubbing for marks, and they changed, what it is, and you see that every single line has been gone and, crossed over just so that they could try to argue for any marks because they didn't know what was going on. I want you to show me what is going on. I expect that you're going to be able to show me what's going on. So when they're not connected, what we will see is going to be a hop over top of there. Okay? That means a not connected line. We are not using this inside of this course. Hop. Okay? Like that. If you do have them crossing, you cannot try to claim to me that this thing is going to be a connection. You cannot claim that it's not a connection. I want to see dots to go and make sure of that. Otherwise, it's just a garbage drawing, and I don't need to mark it, and I probably won't mark it. Okay, power wiring, generally seen as a thicker line. Skinny wiring, generally going to be seen as a control one, but it's neither here nor there. Usually we'll just identify them based upon the voltage that they're going to be connected to. I'll tell if this is 600 volts coming to a motor versus 24 volts control. I'll see what it is, and then I'll make my designation. Also the type of components that are going to be inside of it. Power circuits are going to have the motors, and they're going to go and have the actual contacts themselves. Control circuits are going to go and have the push buttons and things like that. Okay, that is as far in as we are going to go with this one here right now. Schematic and wiring, well, yeah. We're going to move on from there, actually. We won't stop this one quite yet. We're going to take a quick look at what a wiring diagram is and compare that to a schematic diagram, and then we'll actually stop the video where we start to change from one over to the other. Okay, let's start with this. This over here is what in the field you would want to have if you need to go and hook up a motor. Because what this shows, and although it's a black and white one over here, it shows you the actual physical connections, the jumpers that need to be made from component to component. And what it is it is simply just going to be a paint by numbers that we are going to go and have, right? You remember those from when you're a kid, paint by numbers, you know, where they get all the different numbers and you just have to paint over them, and then you can be, look at this, I made this beautiful painting of a horse. And everybody knows it was a paint by numbers, but it allowed you as an unskilled child to go and accomplish something that was way beyond your level. That's what these are going to allow us to do as well, is they allow us as not necessarily understanding what happens, but we can just follow the connections through. There are things that are outside of my scope of understanding and that I'm happy to do off of a wiring diagram because it's just going to make those connections. You will be able to, build these ones though yourself. This is still a pretty elementary one. Let's go through it. If I take a look, I'm going to go and identify my power wiring. I'm going to run these all as red lines. I see that I'm coming into this over here. This is going to be my disconnect switch. They refer to it as a safety switch, but it's going to be my disconnect switch. And it's going to have my fuses. I always have to come into the top side. I'm never allowed to come into the bottom side of those. And if I follow that through, this would be my switch contact off of there. That's the handle they're showing. I carry my power through the fuses, down, over here, where it's then going to go through the contactor. What's inside of the contactor? Well, we know that. It's going to go and have those two sets of points, right, inside of there. And then it's going to come out of the contactor. It's going to go into the overload. This is a physical overload relay that they're showing us over here. But we know that inside of that, we have got the double hook thing like that. And then it is going to go and carry through to my motor itself. So what we're seeing is that we have got a power line. This makes it easy for me to go and do my connections, because when I'm hooking up my motor, I'm going to have my 3-conductor cable. I'm going to take my 3-conductor cable into this cabinet that I'm going to go and have, my magnetic starter cabinet. And I'm going to go and take one of my lines to T1, one to T2, one to T3. That's as much as I need to do, is take a look on there. Same with my safety switch over here. Take my 3 lines, my cable in, and I connect them in there. Same with this one over here. All I need to do is identify where do each of the 3 lines that I'm taking in from that cable all end up on, and make those connections. We don't need to necessarily, follow them through all the way on the lines. They should be followed through. They're going to show that. But in some cases, they're also going to go and use bust connectors. Maybe we'll talk about that stuff a little bit more inside of drawings there. I think, 4th year we talk a bunch about bust connectors. So we follow it through. We just use it as a paint by number. When it comes to my actual connections inside of here as well, all of my control connections are done the same way. I can go and follow a line from here. I can see that I've got, hold on, look at that, 3 wires. Just circle that over there. 3 wires going up to my stop-start station. What type of control is this? You should be familiar with this, that we call this 3-wire control, because we only need to bring 3 wires up to that stop-start station over there. So I've got my 3 wires up there, and I can go and identify which terminals I'm going to put them onto. My start button is going to have 2 terminals. My stop button is going to have 2 terminals as well. And then I can figure out what the other sides go to inside of each of these. Really easy ways for us to troubleshoot and get there. It is a tough drawing to make though, because we get pretty decent at making this. This is the exact same diagram. Following that one line. Remember that red line we traced? We went through a disconnect switch, through the fuse, all the way down to the contactor, through the overload, all the way to the T1 of the motor. We followed that through there. It just was a more complicated path on this diagram over here. But ultimately, it achieved the exact same thing off of it. So we follow it through off of these ones here would develop, usually working off of these schematic diagrams, also referred to as my ladder diagrams, or sometimes elementary diagrams. But I'll lay out the electrical interconnection. Not the physical, but just the electrical interconnection off of these ones. We work from this, and then we need to take it back into these ones over here. And it is a complicated manner. We're going to do that in the next video. So for now, we'll just stop this one here because we're a half hour in, and that way it doesn't make this one video too long.